Glenn experts continue using state-of-the-art analytic techniques to attain a greater understanding of the physical phenomena encountered during a typical shuttle flight. Although RCC is very strong, the inner carbon structure can oxidize if exposed to the high-temperature re-entry gases. This can weaken the structure. Thus, the integrity of the oxidation barrier coating on the carbon is critical. Glenn experts, together with colleagues at Johnson Space Center, found zinc from the peeling paint on the launch structure could lead to pinholes, one type of possible coating degradation. Despite many improvements in external tank foam design, foam shedding is an ongoing concern. Glenn researchers were able to perform wind tunnel tests of external tank components to address this problem. Insulating foam keeps the extremely cold liquid oxygen and hydrogen propellants inside the external tank from causing atmospheric nitrogen and water vapor to condense on the tank's surface, forming thick layers of ice that could also break off and strike the orbiter. To mitigate the risks of foam shedding, NASA's flight engineers are investigating eliminating or minimizing as much foam as possible. The protuberance air loads, or PAL ramps, wedge-shaped pieces of foam that reduce turbulence over the cable trays on the liquid hydrogen and liquid oxygen portions of the tank, were identified as foam that might be eliminated. NASA Glenn engineers were asked to run tests in the center's 8x6 supersonic wind tunnel. By modifying existing designs and hardware from similar tests run in 1983, and by working an extended schedule, the fabrication team and the 8x6 team were able to design, fabricate, and install the model and run the first test of the liquid hydrogen PAL ramp just 6 weeks later. A second model, built to test the liquid oxygen PAL ramp, uses dynamic pressure transducers under the cable tray to measure the aerodynamic turbulence causing flexing of the cable tray during simulated launch conditions. Changes to the cable tray hardware configurations are being tested to minimize the effects of turbulence. Because of the efficiency and dedication of the 8x6 staff, the fabrication staff, and other NASA team members, PAL ramps may be modified or removed entirely for STS-114, the next shuttle launch. Space exploration will always remain a high-risk venture, but NASA is devoting tremendous effort to avoiding conditions like those that led to the Columbia accident. NASA has called upon the Glenn Ballistics Lab, a facility unique in the agency, to continue its testing. The lab is acquiring data and calibrating computer models that, in the case of another orbiter vehicle foam impact, can be run in real time to trigger on-orbit inspection and repair when needed. Glenn scientists are also using what was learned from the Columbia breach to help develop some of the components in an on-orbit RCC repair kit that will fly on the next shuttle mission. If a breach of an orbiter leading-edge panel is suspected in the future, real-time testing analysis will be performed on the ground, while onboard cameras or satellite imaging examine the actual damage. An astronaut will then exit the vehicle to inspect the breach, evaluate the risks involved, and repair the damage if possible. An integral part of that repair kit will be Grabber, a Glenn-developed and manufactured refractory adhesive material. Grabber can repair RCC cracks of up to 1/2 inch. It has also been tested as an adhesive and sealant in several repair kit concepts, including a set of leading-edge replacement panels, an inflatable fabric balloon, an umbrella plug, a patch, and a metal alloy or treated fabric wrap. Grabber has a peanut butter-like consistency that doesn't foam or bubble in vacuum. Johnson Space Center is developing a gun and troweling tools to apply the material in the challenging conditions of space. A number of critical properties such as viscosity, working life, and behavior on hot and cold RCC surfaces are being evaluated. Grabber cures within 2 hours at 100 to 120 degrees centigrade and can withstand the high temperatures of re-entry through plasma. Most repair concepts are designed to repair small cracks or holes. The Glenn-developed metal alloy leading-edge wrap has been conceived to repair a large hole up to 16 inches in diameter. As one of the 5 repair kit concepts under consideration, this refractory metal is a flexible material that can withstand the heat and stress of re-entry and must also be coated to prevent oxidation. Materials researchers are conducting tests to add coatings and assess their efficiency to overcome effects of cracking when the metal is bent and heated. Currently, Glenn personnel are involved in an agency-wide team effort to determine the effects of aging and service history on RCC microstructure and ultimately its mechanical properties. An integral component of this is the use and development of suitable non-destructive evaluation techniques to screen for internal structural integrity even when panel surfaces appear intact. Engineers in the Glenn Ballistics Lab are testing foam, ice, and ablator impacts on RCC panels to validate all of the analysis models developed for impact damage to RCC. An ongoing multi-center analysis effort is running hundreds of analysis production runs to establish critical threshold damage limits to the RCC leading edges due to debris impacts. Orbiter windows are also undergoing impact testing of aluminum oxide particles, butcher paper, copper, ice, and ablators. NASA return-to-flight team members didn't stop with the known accident scenario, the foam strike and the rupture in the leading-edge materials. The work went on, beyond impacts. The problem resolution team, composed of members from Johnson Space Center and shuttle program contractors with support from Langley Research Center and NASA Glenn, looked at other possible failure scenarios not related to the Columbia accident, no matter how improbable. Their investigation discovered an unanticipated phenomenon with grease in the shuttle's non-serviceable rudder speed brake actuators. 20-year-old grease in disassembled actuators from the orbiter Discovery was found to have discolored. This could indicate that the grease may have broken down. It wasn't expected that old grease would do this, and no data existed to explain why. A breakdown in grease could cause corrosion and mechanical failure, a critical situation NASA needed to understand because of the critical non-redundant actuator design. A single fractured gear tooth could jam the compact gear mesh, locking all 4 actuators and resulting in total loss of rudder control. GRC grease tests confirmed that although the grease had discolored, it had not broken down or degraded. Glenn experts understood that wear on gears is probabilistic. Age and flight history cannot be used to reliably predict how long actuators remain safe to fly. After analyzing the damage and wear found on the components in Discovery's actuators, Glenn Tribology and Mechanisms personnel determined there was enough residual risk that the flight vehicle hardware actuators had to be inspected more closely on all the orbiters. At first, actuator team members thought they could use non-destructive evaluation analysis to prove flight readiness without removing the hardware. But NDE analysis found another problem, necessitating a review of existing flight hardware, which was then changed out and replaced. Glenn Aerospace Mechanisms experts then performed in-depth analysis of disassembled actuators that had been flown on Discovery. The analysis revealed gear tooth pitting, fretting, and corrosion, in addition to extreme edge loading on gear teeth, which was weakening them. Before the flight schedule could resume, NASA had to find out why. The problem resolution team discovered a dithering phenomenon that existed only when the shuttle was powered up. Because wear on gears is probabilistic, empirical observation of the dithering phenomenon was critical. Within a week, Glenn Research Center personnel built a dithering test rig that is gathering data to establish realistic actuator life and reliability estimates. These studies will help Glenn and the NASA Engineering and Safety Center to plan a long-term actuator servicing process. The return-to-flight shuttle will fly with fully refurbished actuators.